The engines lesson will be discussed in 9 sections. First will be an introduction. 2 wing-mounted Rolls-Royce engines provide thrust for the 757. The engines are 3-spool, axial flow, high bypass ratio type engines. Both engines incorporate a full authority electronic engine control system, or EEC, which provides a trim input to its associated hydromechanical fuel controller to drive the engine to an EEC-computed command thrust level.
Engine performance indications are electronically displayed on the ICAS screens. Standby engine indications are located adjacent to the ICAS screens. Engine fuel controls and indicators are located on the pedestal. Starting and ignition controls and indicators are located on the overhead panel.
Let's now look at the fuel and oil systems for the engine.
The fuel system is typical of those used by high bypass turbofan engines. Fuel flow indications are displayed on the lower ICAS screen in pounds per hour with a pointer and corresponding digital readout.
A 3-position engine fuel control switch operates a spar and engine fuel valve for each engine. In the cutoff position, the valves are commanded closed and ignition is terminated. In the rich position, the valves are commanded open, and additional fuel is initially scheduled for engine start. The selected igniter or igniters are activated. After the engine is stabilized during start, the fuel control switch is moved out of the rich position to run. Selecting the engine fuel control switch to run also opens the spar and engine valves and activates the selected igniter or igniters.
The spar valve light and the engine valve light are located above the fuel control switches. These lights illuminate whenever there is a disagreement between a valve and the selector position. In addition, an associated ICAS message appears. The ICAS message is inhibited during the engine start. Now let's discuss the engine oil system. The oil system is also typical of most oil systems used for high bypass ratio type engines. The engine oil indications appear on the lower ICAS screen. Digital readouts display the actual value of each indication. The white vertical lines provide a reference to show the normal operating ranges. The white pointers show the relative value of each oil indication. The oil pressure indication has an amber caution band and a red line operating limit. When oil pressure drops into the amber caution range, the pointer and digital readout turn amber. When oil pressure drops below the minimum operating limit, the pointer and digital readout turn red. Oil pressure lights for each engine are located on the center panel below the standby engine indicator. An oil pressure light illuminates when oil pressure decreases below the minimum operating limit for that engine, accompanied by an engine oil pressure advisory message.
Should the main or scavenge oil filters become obstructed, an engine oil filter advisory message appears. This indicates that unfiltered oil is being used to lubricate the engine. Should either filter become obstructed, refer to Operating Manual Volume 1. Located below the oil pressure indicators are the oil temperature indicators. The temperature indicators have an amber band and an upper and lower red band. For starting, the oil temperature pointer cannot be in the lower red band, but may be in the amber band. The throttle may be advanced as long as the oil temperature pointer is not in the amber band. Engine operation in the upper or lower red band is not permitted. Located below the oil temperature indicators are the oil quantity indicators. The quantity indicators sense oil quantity at the tank. The minimum oil for dispatch is 16 quarts. When the pointer decreases into the white band at the lower end of the vertical line, the oil quantity is low. Indicated oil quantity will increase or decrease with power changes. It's not unusual for an engine to gulp up to 10 quarts.
The spar valve light.
Engine operation in the upper.
Now let's look at some additional ICAS indications associated with engine performance.
Located below the oil quantity indicators are the engine vibration indicators, which receive vibration information from the N1 and N3 compressors. Engine vibration is displayed in a vertical format, with pointers and digital readouts indicating the vibration level. During normal operation, the vibration indicators display the compressor with the highest vibration level. Broadband vibration will indicate if any speed signal is lost or if a tracking filter is faulty. When the level of the tracked vibration exceeds 2.5 units, the vibration indications for both engines are displayed automatically, and the engine vibration and pointer of the affected engine change to amber.
Primary indications associated with engine performance are normally split between the upper and lower ICAS screens. White arcs identify normal operating ranges for these indicators.
Located at the top of the upper ICAS screen is the engine pressure ratio, or EPR indicator. The EPR indicator displays actual engine thrust with a pointer and corresponding digital readout. EPR is used as the primary indication for setting and monitoring engine thrust. When the throttles are moved, the difference between the commanded thrust and actual EPR is displayed as a white arc. The command sector disappears as the actual EPR approaches the commanded EPR. The command sector aids in visually monitoring engine acceleration or deceleration. A computed thrust limit is also displayed as an amber line on the periphery of the EPR indicator. This limit is the maximum thrust for all phases of flight and varies with existing ambient conditions. This value is acquired from the electronic engine control, or the thrust management computer, when the electronic engine control is off or in op. With the electronic engine control thrust limit protection operative, the throttles can be moved to the forward stop, and the engines will not exceed the displayed limit.
In addition to the computed thrust limit, the selected reference thrust setting is displayed as a digital readout and reference bug. Reference thrust will be discussed in detail in the thrust management system.
Located below the EPR indicators are the N1 indicators, which display the percent RPM of the N1.
A moving white pointer and a digital indicator show actual N1. At the top of the arc is a red radial line indicating the maximum operating limit. N1 operation at or above this limit will cause the digits and pointer to turn red. Located beneath the N1 indicators are the exhaust gas temperature indicators. When EGT enters the caution range, the pointer and digits turn amber. When EGT exceeds the red line limit, the pointer and digits turn red.
Maximum EGT during engine start is 570 degrees, as indicated by a red line. The maximum EGT line is displayed until the engine is stabilized at idle RPM.
During takeoff or go-around, engine operation with the EGT in the caution range is permitted for up to 5 minutes. The EGT caution range is inhibited for 5 minutes once the amber range is entered.
The N2 indicators are located at the top of the lower ICAST screen. The N2 display, which shows the percent RPM of the N2, is identical in operation to the N1 display. Located beneath the N2 indicators are the N3 indicators. The N3 display, which shows the percent RPM of the N3, is identical in operation to the N1 display. When N1, EGT, or N3 reaches or exceeds the red line operating limit, the exceedance value appears in small white numbers below the large digital readout. The numbers in the box turn white when the value decreases to normal. This exceedance information is automatically recorded by the ICAST systems.
The digits are erased from the ICAST display by pushing the max indicator reset switch on the ICAST control panel. Although this removes the exceedance indication from the ICAST displays, the information is stored for maintenance use. If either of the ICAST screens fail, all engine parameters will be displayed on the remaining screen. A standby engine indicator with a 2-position selector is located on the captain's panel.
In the auto position, the standby indications are displayed automatically when there's an ICAST failure, normal AC power is lost, or on the ground when either ICAST screen has failed and the status page is selected.
Positioning the selector to on displays the standby indications at all times. Maximum limits are displayed in red on each side of the instrument. The white arc or command Now let's look at the ignition system and start systems. The controls and indicators for the ignition and starting systems are located on the overhead panel and the pedestal.
There are 2 igniters per engine with no time limits. Either the number 1, number 2, or both igniters may be selected.
The start selector is a 5-position switch. Click on the left start selector to select the ground position.
Selecting the ground position opens the starter valve and arms the selected ignition circuit. The selector is magnetically held in this position. When the fuel control switch is set to the rich or the run position, the ignition circuit is completed to the igniter. At approximately 50% N3, power is interrupted to the start selector and it moves to the auto position. This deactivates the ignition circuit and commands the start valve closed. The engine start valve light illuminates when the start valve is not in the commanded position, or the valve is open with N3 RPM above 50%. In the auto position, if the slats are extended or engine anti-ice is on, the selected igniter operates continuously.
Selecting the continuous position provides continuous ignition to the selected igniter. The flight position provides ignition to both igniters, no matter which igniter is selected.
With the start selector in The start valve light indicates the starter valve is.
The flight position commands.
Next, we'll discuss the EEC and the ELC. Each engine EEC, or electronic engine control, is powered by dual dedicated generators. The EEC continuously computes the maximum limits for thrust. During normal EEC operation, each EEC provides a trim input to its associated hydromechanical fuel controller to drive the engine to an EEC-computed command thrust level. The plastic-guarded EEC switches are located on the overhead panel. When the EEC switch is selected on, the electronic fuel control trims fuel flow for EPR limiting. The in-op light illuminates when the respective EEC is inoperative or the EEC is selected off. When the EEC is inoperative or selected off, there is no longer any overspeed protection, and the fuel control unit operates independently of the EEC. Full forward throttle will now produce an engine overspeed.
When an EEC failure has occurred, or the EEC selected off, the command sector will not be displayed. The maximum N1 reference is now acquired from the thrust management system.
EEC failure causes the respective EEC to maintain current thrust until the affected EEC switch is selected off. Before selecting the EEC off, the respective throttle should be retarded. This would prevent a possible engine overspeed. With one EEC selected off, throttle stagger will occur. The thrust control system also includes an electronic ELC, or engine limiter control unit. Each engine ELC is powered by dual dedicated generators. The ELC provides N1 RPM limit protection. When operating at or near any limit, the thrust should be reduced before turning the ELC off. Otherwise, a momentary overspeed condition could develop. Each engine EEC.
Now let's discuss the thrust management system. The thrust management system computes a thrust reference limit for manually setting the throttles, or to control the auto throttles when engaged. Thrust management inputs include altitude and temperature data from air data computers and the desired mode selected by the pilot or the flight management computer. Thrust modes are selected manually from the Thrust Mode Select panel, located on the center instrument panel. Thrust modes can also be automatically selected by the FMC when VNAV is engaged.
Selectable thrust limit settings are takeoff, go around, climb, continuous, and cruise. Derated thrust limit settings for climb may also be selected. Additionally, Climb 2 provides an alternate derate feature for noise abatement during takeoff climb-out at noise-sensitive airports. Thrust level is reduced to maintain a 1.2% climb gradient with one engine failed. This feature is armed when the 2 button on the thrust rating panel is pressed on the ground before takeoff.
The selected limit is displayed as a digital readout and a green reference bug. On the ground, the takeoff limit is automatically displayed. Pressing the takeoff go-around switch while airborne displays the go-around limit for go-around thrust.
The go-around thrust reference limit is automatically displayed when the flaps are extended or glide slope is captured.
Click on the appropriate switch to display the max climb limit. Click on the appropriate switch to display the max climb limit. Click on the appropriate switch to display the max continuous limit. Now click the appropriate switch to display the maximum cruise thrust limit. A thrust reference selector located on the ICAS control panel overrides the thrust management system to manually set the thrust limit.
Pulling out on the inner control allows the thrust limit to be set manually, and the letters MAN appear as the mode enunciation. Rotating the selector sets the desired target EPIRT. Autothrottles do not use this target value. The outer control selects the EPIR indicator to be set.
The autothrottles do not. The thrust reverser system is discussed next. Each engine's thrust reverser is powered by its respective hydraulic system. Loss of a hydraulic system renders the affected thrust reverser inoperative. The reverser lever has three positions: full down, interlock stop, and reverse thrust. When the reverser levers are in the full down position, the thrust reversers are locked in the forward thrust position. Before the reverser lever can be raised for reverse thrust, the aircraft must be on the ground and the throttles in the idle position. Moving the reverser levers to the interlock stop position causes the throttles to lock in the idle position. A signal is sent to the respective reverse isolation valve, causing it to open, supplying pressure to the reverser. The reverser then unlocks, and hydraulic actuators move the reverser cowl aft.
An amber reverser enunciation appears above the EPIR indicator as the reverser cowl unlocks and all forward thrust reference displays disappear. When the reverser cowl and blocking doors are fully extended, the reverser enunciation turns green and the interlock stop releases. The reverser lever can then be moved upward and aft for reverse thrust. In reverse, the EEC downtrims the fuel control for thrust limiting. An auto stow system is incorporated in the thrust reverser system on 757s and 767-300ERs. If a reverser becomes inadvertently unlocked, the auto stow system automatically sends a signal to open the respective isolation valve supplying pressure to stow the reverser. Now try some questions. Now let's look at in-flight engine shutdown.
With an engine shut down in flight, selecting the fuel control switch to cut off causes the in-flight start envelope and start reference cursors to appear on ICAS. The in-flight start envelope displays the present altitude and the recommended airspeed range for starting. Altitude and airspeed ranges at 2,000-foot intervals below present altitude are also displayed. If the aircraft is above the start envelope, ICAS displays the highest altitude for which an in-flight start can be accomplished. The in-flight
Now let's look at 767 differences. The 767-200 and 200ER airplanes are equipped with two General Electric or GE CF6-80A engines, whereas the 767-300ER airplanes are equipped with two General Electric CF6-80C2 engines. System design and operation are generally the same as the 757 engine. The primary differences are the engine indications and various system values. N1 is the primary indication for setting thrust. There is no EPR indication.
standby indications for the GE engine are liquid crystal displays on N1, N2, and EGT.
The 767 GE engines are not equipped with engine limiter control units.
The minimum fuel-on reference indicator is located at 15% N2 for the GE engines.
The maximum starting EGT limit for the GE engines is between 750 and 870 degrees centigrade and is represented by a red line during engine start. The line disappears when the engine stabilizes at idle. Now try some questions.